Okay, so have a line, we have a point on the line, we have a vector in the direction of the line. They said the same thing twice, so. That allows us to get the equation of the line. And we're gonna have a point X, Y, Z. I'm gonna write a test to see whether point X, Y, Z is on the line or not. Okay. Put a few symbols in this. Same notation I usually open with. Point on line X naught, Y naught, Z naught. So we could posit this vector, which we might or might not use depending on mood. Here's the vector X naught I plus Y naught J plus Z naught K. Right? Okay. Now we have I made that point look like it's on the line. Let it draw it a little bit off the line. And you can assume that maybe I intended to draw on the line and I just missed. Or maybe I didn't intend it to be on the line. Wherever X, Y, Z is. That way. Yeah. Now my arrow in the label up to this vector has to cross over that vector, but we'll live with it. Okay. And we'll call this vector first of all, this vector I'm going to label B. And just a vector I'll label this W. Okay. So B has three components. Okay. So we call those components A, B, and C. Now we've already seen that much, but not in quite as detailed a picture. W equals what? What's the X component of W? Or the I component? Well, to get from here to here, X has to change from X naught to X, right? And Y has to change from Y naught to Y. And the Z value has to change from Z naught to your general Z. And it follows the W then equals this. Okay. Now, we can prove that. I'm gonna call this vector R naught, R sub zero. Okay. So I can actually write a proof that W has to equal this because this vector I have to squeeze it in there so you get a bigger picture. This vector is xi plus yj plus zk. It's a vector from the origin to the point x, y, z. I'm going to call that vector R. So I can prove that what I just said is true. It's a very simple proof. The R vector is your R naught vector plus your W vector. Okay. Now, if you just write out what that means, you just write out the details. R is xi plus yj plus zk. Well, I'll write it out, but yeah. I say you should write it out, I honestly won't. Because you probably know. R, this vector. I'm sorry, this vector equals R naught, this vector, plus the W vector. Okay. X naught I plus Y naught J. R, Xi plus Y J plus ZK equals R naught, X naught I plus Y naught J plus Z naught K plus W. So that W equals this vector minus this vector, which is going to give you this. Just trivial, just rearrange. Solve for W. And now we're pretty sure that we got it right. It's value being able to write out simple proofs. You're going to totally verify that what you've done is correct. That's a proof. Okay. It's actually a fairly trivial proof. It's not totally trivial because you got to process that picture. Okay, now. X, Y, Z is on the line if and only if W is parallel to B. If W is parallel to B, then the path from here to here is parallel to the path up to the vector B. That's exactly what we mean by being on the line. Okay. Now, what's the test for W being parallel to B? That occurs if the cosine of the angle between B and W is 1 or or -1. Okay, in other words, 1 on this side, -1 on that side, right? The angle between B and W is 0 if W is on this side and on the line. Negative, well, sorry, cosine of the angle between B and W are parallel. That means that the angle is either 0 or 180 degrees, 0 over pi. Okay. In which case, cosine of theta has a magnitude of 1. So the magnitude of this has to equal the magnitude of this. Then you can write this out. And I'm not going to write it out, but you could write out the symbols and get to the equation of the line just from this. Okay. Or the big frost W equals 0. You could write that out and get the equation of the line. It's worth actually doing that. It won't take a minute if you know what to do. And if you don't have a clue how to start, well, okay. There it is. Okay. Or W is a multiple of Z. And that's the easiest way to get it. Okay. In this case, there's this T such that W equals T times V. Parametric equation. Parameter is T. You should be reviewing chapter 11. Okay. Makes more sense. Then you're going to need project. Okay, so W is TV. Well, we don't have room here. Let's use W equals TV. It means that this W vector, X minus X naught I plus Y minus Y naught J and so forth, has to equal T times your V vector, which is AI plus BJ plus CK. Well, the I components have to be equal. So we get 3 equations out of this. All 3 of those equations are solved, you're on the line. Okay. So right here, if you wish, is an equation of the line in 3 parametric equations. They can also be written as T equals X minus X naught over A equals Y minus Y naught over B equals Z minus Z naught over C. And you could ignore T now. And this triple equality, which comes down to 3 equations again, This says X minus X naught over A equals Y minus Y naught over B. And X minus X naught over A equals Z minus Z naught over C. Y minus Y naught over B equals Z minus Z naught over C, which is exactly the same as these equations. Okay. Five. Simultaneously equations. So you can even use some of the techniques you're learning in linear algebra for help. Okay. So parametric equations of the line, call this symmetric equations of the line without the t. We don't need to. There's the picture. And really the picture could come down to just right. Instead of X naught, Y naught, Z naught, just call the point P naught. And the vector V. And your arbitrary point P. And make these vectors. So, you know, P naught is a vector from the origin out to this point. P is identified with the vector from the origin to this point. You could really condense it all down to this picture. You might want to think about how you would do that, because that's an important way to think about mathematics. Okay. If you can condense it down to the simplest possible picture and then build everything up from that picture, then you don't have to remember as many details. You also exercise your ability to put things together and to follow from a premise to a conclusion. Okay, I kind of recommend it, but once you do the problems, you're okay. I think you'll be better off on tests the more of this you learn to do, rather than just doing things out of habit. But I mean, if you do it perfectly out of habit, you're still going to ace the course. That's your only goal. It might be the only practical goal you have because of all the pressure you're under. Then I'm okay with it, but I'd rather you learn it more deeply. Okay? That's just for yourself. And for the sake of all the wonderful engineering you're going to end up doing in your life. Okay? Okay. Now, there's another picture. For planes. And I'll start with the most abstract picture. Here you got a point P. I'll use a vector to indicate we think it was a vector from some origin out to this point. So I can talk about adding multiples of B to T and stuff like that. Okay. And so we have P. Now, sorry, this is P naught. This is a point on your plane. And here's a point P in your plane. Okay, or at least the point you want to test to see if it's in the plane. And now we have a vector. We'll call M. Normal. Normal. Yeah. Okay. Somebody out my home bubble or something. Something about abnormal or something like that. They were looking at me when they said that. I don't. Okay, makes sense. I'm not what I just said. picture. Now, what's conditioned for P to be in the plane that passes through the point P naught perpendicular to the vector M? Okay, put an equation for the plane perpendicular to M containing the point P. Point P is on the plane. What's the condition for the point P to be on the plane? Say what I said a minute ago. Maybe I don't have a ball. Okay, so let's say we want a plane through this point perpendicular to this vector. Okay. So I hold this vector out, take this plane, and I adjust it so it matches the base of the vector. And now the plane goes through this point perpendicular to this vector. Now we want to test whether some other point down here is on the plane. So what should be your test? I think we maybe have an answer, so let me pause. See what the thought is. So we tried to talk about the cross product of the P naught vector and the N vectors and perpendiculars, but P naught depends on where your origin is. Okay. So vector from the origin out to here doesn't have to be perpendicular to N. What has to be perpendicular to N? What in this picture, what could I sketch very easily in this picture does have to be perpendicular to N? Okay, what has to be perpendicular to N? Well, any line in the plane, okay, has to be perpendicular to N. That's what we mean by a plane perpendicular to the vector N through a given point. Okay, so we've got a good answer. There's a partial answer, the dot product of P with N, and that quite get it because the vector P is the vector from the origin to P. That's why we've defined it today. Because we're identifying the point with that vector, okay? But then pretty quickly, we saw the modifications and versions. Okay, dot product of P minus P naught with M. The dot product of this vector because this vector lies in the plane. They said any line in the plane should be perpendicular to N. Yeah, that's equivalent to saying any vector that lies in the plane or any vector that's parallel to a line in the plane, if you wish. Now, this vector is drawn so that it is in the plane, but it's on a line in the plane if it is, people get on. So, we can work through all the technicalities, but vector P minus P naught is in the plane. And remember, you've got an origin out here someplace with a vector from here to here and a vector from here to here. And the vector from here to here minus the vector from here to here is this vector. And that's because this vector plus this vector equals this vector. And it just simple algebra. And it's a little confusing to visualize that until you've done quite a bit. Okay. But think about it. Okay. Okay, so Normal vector is AI plus BJ plus CK. P naught X naught I plus Y naught J plus Z naught K. In other words, the point P naught has coordinates X naught, Y naught, Z naught. Okay. And point P has coordinates X, Y, Z, so that the P vector origin out to the point is Xi plus YJ plus ZK. Then, how do you write the fact that the two vectors are perpendicular? Well, first of all, P minus P naught has got to be perpendicular to M, meaning perpendicular to AI plus BJ plus CK. Well, what's a vector P minus P naught? Think it. Not even going to ask you to answer, but give you a second to process it. Okay, well, the vector P minus P naught should be obvious, but again, you know, you haven't been dealing with vectors in this context that long, so it's not going to be that. It's going to be X minus X naught I. This vector, if I put in parentheses, dotted with this vector, S equals 0. Well, go ahead and write it out. Do the dot product and set it equal to 0. Should take you just a minute. Okay, depending whether you write fast or not, you probably have it or you're on the track. At least you should probably see what it is. I mean, the dot product is X minus X naught times A, so I'll write that as X times X minus X naught. And B times Y minus Y naught. C times Z minus Z naught equals 0. Okay. Now, just kind of a neat aside, since half the class is taken linear algebra, the other half is already taken. You'll need to combine this to 2 dimensions, 3 dimensions. You do this in any number of dimensions. Rather than want to use alphabet A, B, C, rather want to use like A1, A2, A3, and so forth. Okay. And you don't want to use X, Y, and Z. Maybe use X1, X2, X3, X4. And then I'm not sure what you do about X naught, Y naught, and Z naught. You probably use some different symbol. Okay. Because of the X1, you know, if you go into a bunch of dimensions, but you can write the equation of a hyperplane just by extending this, because the vectors just extend by, instead of I, J, and K, you probably one of the standards E1, E2, E3, up to E7,988,263 if you're in a space of that many dimensions. If you're doing data analysis, heavy duty data analysis, that would be kind of a small space. Okay. And you'd apply techniques of linear algebra very powerfully. Okay. Many things can be modeled linearly by hyperspaces. Spaces way out of roughly 3 dimensions. And they look just like 2 and 3 dimensional spaces. When you write them out, they're just longer. It's more terms. So you'd have, instead of 4 terms here, you'd have 7,598,392. That's what I said before, and I'm sure it isn't. Okay. Makes sense? To be a big long equation, and you code that. course, I don't know in the future, you probably just ask an AI to do it, and then you wonder, what's the use of having learned all this stuff? Well, you gotta keep an eye on the AI, so if you don't know the stuff pretty well, you're not gonna be able to do a very good job of keeping an eye on the AI. I don't know how that's gonna evolve. I mean, it's new right now. But it's, people are saying it's equivalent to the Industrial Revolution. I don't see why it's equivalent to even more than that. Why it's not. Okay, but I don't know. I've seen a lot of, like, one thing that I thought was pretty incredible. Okay, when I came here, when we were 51 and a half years ago. Okay. But as an undergraduate, I was in a fraternity. They may take ties with fraternity as a graduate to like a coach or something too. That wouldn't allow me to swim. Plus, you know, everybody just died laughing at my stroke. No. Actually, I kind of won my races, but it was against bad competition. Great stuff. Very good. The year, I think after I graduated, they got this electronic machine that they would use to do the number crunching in their labs. No such thing as desktop computers at the time. Okay, the equivalent of what's in your phone probably would have covered several square miles of the technology they had in those days. When I started there, they gave us a tour of the computing center. Okay, it was close to the other side of the football field, close to the gym. It's a good sized building, just a bunch of tapes. Okay, hanging on the walls, and they take a tape off and run it through. And they had this IBM 1107 computer, which was state of the art, which, yeah. Well, they're going to send a man to the moon with computers about like that. Okay, I can't even describe something that would be equivalent to. It's so primitive. Think of the most primitive cell phone that's ever been. Okay. And that was, you know, 1965, 59. Okay. 59 years ago. Yeah, that's fine. That time. Which is strange because I'm only 32. You tell that by looking at me. Okay, so anyhow, it was an analog machine, but it had some electronic components. It's called the Freedom. Name the company that manufactured it. And it saved people time because we were using sliders. And we were good at it. You had to be, you died if you didn't, if you weren't. You had to crunch a lot of numbers, and you can't do them by hand. You do it quickly in a slide rule if you're any good at it. And we all got good at it. Okay. A couple of years later, I finished graduate school, and graduate school finished with me. I don't know which way. Okay. I started applying for jobs. I got one here. Physics lab was over in the other hall where there was a kind of physical therapy lab or something. Moved over here about 15 years ago. Just a little bit. And the electronics program went belly up. This is the electronics lab. But over in that lab, on the wall, on these very tables, probably that one right there, they sat this machine about the size typewriter, if you've ever seen one of those. Okay, yeah, but this. And you could press buttons, you know, just a keyboard, square root of 738. And the lights would flash for a couple of seconds and it would come up. That was the most amazing thing I'd ever seen. the most amazing bit of miniaturization I'd ever seen. It blew my mind. And the thing didn't cost very much. $3,600 in 1972 dollars. To equivalent about $30,000. Okay. It was him along the middle of me, but you know, what before your grandparents' time, I guess. But, to watch how we evolved from that in a few years to handheld calculators. It only cost a couple $100. It's like 1,500 in today's money. And people started bringing them to class and using it, which I thought was great. Okay. And you know, that $3,600 machine in a few years just became obsolete. And from there, the advances we've had coming here, desktop computers came along a couple of years later, very early Apple Cs. Okay. And then go 15, 16 years later, first Windows machines. And I evolved into everything. And now all of a sudden, boom, here comes AI. I've seen incredible changes in what's turning out to be a fairly long lifetime, at least. Okay, haven't hit any limits yet, but you know, drop that in a minute now. Yeah, anybody can. Probabilities increase. You probably understand that. Now I know a little bit about how that stuff works. You know, active neural networks came around 30 years ago. I programmed a couple. They're just very primitive to do something simple. So, okay, I got the idea. Got a son-in-law as an active researcher in the field. Another son-in-law was contact with, but he's really smart too. And then people even smarter than them. Then, of course, you got North Korea throwing a lot into it, so that's a little worrisome. Hopefully, what they do is they use it to make North Korea a paradise, so they don't have to be so obnoxious. I'm not sure that's the way it's going to go there. Okay, well, that's enough about geopolitics. Now, does this make sense? I'm not sure how what you're learning now is going to fit in with everything else. But I'm sure wherever you transfer after you've done here, we'll try to get a handle on it. And you're going to spend the rest of your life trying to keep up with it, trying to learn how to use it. So learn what you do here well as you're doing, as I'm sure you'll continue to do. Okay, well, that's all you need about equations and lines and planes. Well, there's more to it. How do you intersect a line with a plane? That's what we're talking about. So let's do that. And I'll actually use numbers instead of symbols, because if we use symbols, we need an AI plus BJ plus CK for the plane, and we need one for the line. So we're going to have to start subscripting the A's and B's and C's. And I'll just do numbers, but you'll probably work it out symbolically yourself. So you learn just how painful it is to try to figure out a good notation. All right. That's painful to me. I don't know about you. So let's say we've got, I don't know, let's vote. You want parametric or symmetric equation of the line? Symmetric. Parametric. Symmetric. Boy, y'all got to get better with parametric equations because it's way simple. Way simple. It's simple enough either way. Okay. I was going to write symmetric equations anyhow, just to be mean, but I thought I would give you a chance. Okay, so we got X minus 5/3 equals Y minus 2/5 equals negative. That'll be, I'll write it. 4 minus Z over. Okay, now where is this line? What can you tell me about that line? I mean, it's new to you, yes, so I don't expect miracles, but I'll give you a chance. Okay, we had a couple of false starts to a point on the line, but somebody came up with 872. Wasn't the point I was thinking of, because it's an easier one to find, but that's not hard. Okay. If the numerator here is 3, and the numerator here is 5, and the numerator here is 2, then you're going to have 1 equals 1 equals 1. That's good. Okay, and that turns out to be 872. Very simple. If your numerator is going to be 3, X better be 8. If the numerator here is going to be 5, Y better be 7. If the numerator here is going to be 2, Z it better be 2, right? So there's a point on the line. It wasn't hard to find that. It's a good thinking. Okay, we got another individual offering an answer. Okay, and then the other one was, the next one should be pretty obvious. 5, 2, 4, because you make them all 0. So you don't even have to worry about the denominator. You had to worry about the denominator to get this. That wasn't a big worry. It was easy. Even easier. Look at this. Okay. So I'm glad we have 2 points, because now we can check. So either of these points works just fine. Everybody give me a vector parallel to the line. Now, if I had that board that we did earlier visible, you could look at it and figure it out, but that's a little tough. I'll give you a chance. Okay, we got it. Traditional answer. I'll use IJ in the case at 3, 5, -2. If you remember what we did earlier, and I'll just bring it up here. And there's no reason we'd expect everybody to remember all of this until they work the problems. That's why you work home with problems. But parametric equation, or the symmetric equation, is X minus X naught over A equals Y minus Y naught over B equals Z minus Z naught over C. A, B, and C were the components of your vector V here. So before I wrote it, okay? And X naught, Y naught, Z naught were these numbers, okay? So three I plus 5J minus 2K. Okay. And let's say your plane is right, I, J, and K equals what would make it this way. Make it 120. Okay. Now, ultimately, what we want to do is we want to intersect the line with the plane. We're going to kind of get a picture. I mean, we can do the algebra. and not have any kind of an idea of where it is. And of course, that's what you have to do if you're working in 7 million dimensions. If you're working in 7 million dimensions, you better hope everything's linear. Otherwise, you get a lot of impossible topology. Okay. And I don't know much about topology, but know something. Okay, so anyhow. So we've got this plane. So do you know what the normal vector is to that plane? Can you give me a point in the plane? Okay, so let's come back in. We're trying to figure out what the normal vector is, or what a normal vector is, right? If we use any normal vector. We're going to use the most convenient one. Hang on a minute. I think we got a comment or question. Okay, so my question is, here's how we develop the equation of a plane. This is the general form of the equation of a plane. It's the simplest form. Okay. Now this is quite in this form. But my question is now, what was the normal vector? Okay. So let's look. Well, what do you know about the normal vector in this development? It's AI plus BJ plus CK. What are the important symbols? A, B, and C define your normal vector, right? Yes, that was our premise. Okay. Now, where do A, B, and C appear down here in this equation? A is multiplied by x minus x naught, B by y minus y naught, C by z minus z naught. Why? Because x minus x naught I plus y minus y naught j plus z minus z naught k is a vector from Q naught to P. Okay. It's a vector that we presume to be lying in the plane. Okay. Or it's a vector we test to see if it lies. And we dot that with the normal vector, and then this comes out. It's very straightforward product. I'm sure everybody's fine with that. Okay. Where are A, B, and C lurking within this equation? Well, you can see that what's going to be in front of x if I expand this equation? A. Whatever in front of x is A. Okay, so x5. Okay. And B is going to end up in front of y, so B is going to be -4, and C is going to be 6. So if you're given an equation like this, you can just read off the normal. Okay, you understand that? Okay, now we could have expanded this. I'll even write that out because we're actually, everybody's doing so well, we're ahead of the curve here. We have time to mess around. You won't always use this, but you get AX plus BY plus CZ equals AX naught plus BY naught plus CZ naught. Okay. And this is just a number. This is the variable part of your equation. So AX plus BY plus CZ is right. And then this number is what you get from AX naught plus BY naught plus CZ naught, depending on what point you choose. Okay. Well, let's kind of test that out. We can use this point. Well, first of all, let's read off A, B, and C. That should be clear now that A is what's in front of X. this is normal. So also is any multiple of this, any non-zero multiple of this, right? Because you multiply a vector, you don't change the line on which it lies, the direction. You might reverse the direction if you multiply by a negative. But you still are going to have a normal vector. Okay. And for a plane, doesn't matter which normal vector you use. When we get to surfaces, you want the outward normal to deal with that when we get there. Okay. This is normal. Now this number should be AX naught plus BY naught plus ZZ naught. Okay. Can you give me the coordinates of the point that lie in this line? Okay, so I have to put coordinates for points that lie in this plane. And somebody came up with 2400. How'd you do that? Well, y and z are both 0. Then 5x has to equal 120, so x is going to be 24. Okay. Okay, somebody else made it work. So well, you do the same thing with any single. You can let the other two be 0. So for example, you get x and y both 0, 6 equals 20, 6 equals 120, z equals 20. So 0, 0, 20, right? So now you've got the intercepts, and now you can kind of sketch the plane. And that's sort of what you might sketch this thing. Okay, so what you're finding is the axis intercepts. Get the x-intercept, that occurs when y and 0 both 0. And that's going to be 24, 0, 0. Y-intercept could have 0 here, 0 here, and negative 4y is going to be 120, so that's negative 30. And then you're going to get 0, 0, 20. Okay. 24, 0, 0. Let's just say that's here. 0, negative 30, 0. Maybe that's about there. And 0, 0, 20 would be about here. So now we can draw this triangle. It's part of the plane, and we can visualize the direction of the plane. Make sense? You understand all that? Need to process it? Now you're going to see pictures like that. WebAssign shows you too many pictures and asks you to construct too few because you really, it's not equipped to construct a picture. You can sketch a picture. WebAssign apply enough intelligence to interpret it, although if they decide to really invoke AI, you use a sketch pad to sketch the thing and it can tell you that's good or that sucks, or you can make this change, or it can even coach you. Okay, that's common. You see that kind of stuff before you finish your undergraduate education, I think. And on just what the educational philosophy or institution in the department is. They're gonna try to acclimate you to artificial intelligence, so they're smart enough to do that. I mean, they're smarter than I am, so I'm smart enough to have you do that. Everybody knows that. Okay, so anyhow, there we got it. You can even sketch a few. Look at it, really something that is spreading out, right? It's a plane. So easy to find the intercepts, easy to sketch the plane. Okay. So let's see, we're actually, I'm just gonna write down the 24. Right. -30, without writing all the coordinates, just for time. That press, we got 12 minutes, but let's see what we've done. Okay. Then we have this line. Okay. The line goes through. I'll use 872 because the numbers are a little bigger and we've got kind of big numbers here. So we got 8. We've got 7. We've got 2. I've got this little rectangle here. You should be sketching these things. You don't really learn it that well unless you sketch. You don't learn it as well unless you sketch. I'm sure there are exceptions to that, but they're rare. So if you happen to be one, make sure you're right about that. Well, this thing kind of comes out like this. Kind of pointing in our directions, kind of short, but you know, we could extend it if we want to see where this line is. Okay, we can come out here and we can sketch a similar rectangle. I don't know how accurate it is. Okay, something like this. The line's kind of a diagonal, a major diagonal in this rectangle, starting at the origin. And you should be able to make those sketches. So the question is this line ever going to intersect this? Because this thing's kind of coming out like this line's kind of coming out like this. But I kind of think maybe the line's climbing enough that eventually it'll intersect this, but I don't know. I can't visualize well enough to see where it's going to intersect. Although I kind of think it's going to be likely on this side rather than that one, just because of my picture, but I haven't thought that deep. All right, well, you're not going to know, but let's just figure it out. Kind of think it might be in the first octave. If it isn't, it's going to be in the now we have a bunch of simultaneous equations. Of course, everybody knows you can deal with simultaneous equations in a number of ways, I'm sure. I'm not sure. You've been dealing with simultaneous equations in linear algebra? Yeah, you will. I mean, that's what it's all about. Okay. Everything's simultaneous equations, expressed in matrix. As things expressed in matrix form, and some of the things are vectors, and the matrices transform to vectors. It gets really fun. A lot of linear algebras also start off with simultaneous equations, then do vectors, but almost everyone does simultaneous equations and vectors while they get into much other stuff. So I'd say we're going to see this. Okay, so we have makes sense. I mean, those are equations. And we kind of represented those equations. Now, how are we going to solve? How are we going to find an X, Y, Z that satisfies all these constraints? Okay, before I get to that, let me just comment. And this would be profitable to linear algebra students at that thing. Depending how Jason's approaching the course. You could pick any two of these variables and solve for the third one, right? We could let x equal 5 and y equals 3. If we did, we'd have 25 here minus 12 would be 13. And 3z would then be 107. And z would be 107 over 3, which is 3 5 2/3. Okay, I did that quick out of my head, so since sometimes I'm out of my head when I do things in my head. Just do it yourself. Pick any two values, choose which two variables to put them on, you're gonna be able to solve for the third one. That gives you the coordinates of the point of the plane. So you can go to your picture, or you can say, okay, well, it looks to me like a x equals 10 and y equals -10, then z is gonna have to come up about this high, so maybe z would be maybe around 10. Just from that picture. Okay, if you can visualize it, then you kind of test that. Let's see, you get 50 minus 40 plus 30, and it's nowhere near 120. So my guess not really suck. Okay, so that's hard. No, wait, I had minus 10 to be 50 plus 40, which is 90 plus 3. That's perfect. Okay, 10 here, 10 here, and 10 here. I thought I was better than I looked like I was there for a minute. I didn't think I was going to nail it, but it certainly made sense in my visualization. Learn to sketch these so you can visualize them well enough to do that sort of thing. I mean, don't expect to nail it. I certainly didn't. I didn't expect, I did actually. But, okay, so what do you do now? Well, we can start eliminating variables. This has to equal this. We can solve that for x. 3/5 of y minus 2 plus 5. Okay. And it's a little fuzzy head on that. Yeah, just to -6/5. And then we have 5, which gives us plus 24/5. If my head's working, but it's starting to get a little fuzzy. Okay. After nailing that, my brain just gave up. Okay. So maybe that's right. Anyhow, you get x. So now you've eliminated x. And you got x in terms of y. And then you could eliminate z. That's going to be in terms of y, right? So you pick one of these variables, in this case y, solve for x in terms of y, solve for z in terms of y. And now you have expressions for x and z in terms of y. You plug those expressions in this thing and you can solve for y. And once you solve for y, well, you know, you calculate x, you're going to be able to calculate z, right? I don't want to get into the details of that because it take a little too long to write out all the details. And if I skip them in my head, I'm going to make mistakes. Okay, I'll be prone to make mistakes. Get a little bit, yeah, it has this over 4 hours. Yeah. Yeah. 9:32, 1:34. About the end of my endurance, but you get the idea. Does that process seem obvious? How do you see it? Pick any one of these variables and solve for each of the others in terms of that variable, plug them into here, you get that variable you use. Then just back substitute. Okay. You can also set it up as a system of linear equations and solve it by elimination. You're going to learn to do that in linear algebra. So you have a lot of ways that you can end up solving these equations, but right now, this suffices. Okay, so we find the equation where a line intersects a plane. Now, the tough one is, where do two lines intersect? Answer is usually they don't. Take two lines in 3 dimensions, what's the chance that they're going to intersect? Okay. Shoot a bullet this way, somebody else shoots a bullet that way. What's the chance that their paths cross? Much less at the same time. Okay, then we're not trying to get them to cross at the same time. So it's an interesting problem that we'll probably take up next time when we talk about this a little more rigorously. We also want to talk about quadratic surfaces next time. That'll be coming up next week. Sketch these things. Start to develop some sketching skills so that you'll understand the sketches that I'm going to make. You got to learn to look at 3-dimensional sketches. At least sketch a bunch of planes. Just, take 30 minutes, make up some planes, figure out the X, Y, and Z coordinates, and see where they are. Take 2 of them, try to do it on the same set of axes and try to imagine the line on which they intersect. It'd be worth your time when I start talking about quadratic functions, if you have time to do it.